and welcome. This is the 25th S. Dexter Squibb Lecture Series in Chemistry. And so it's a great honor to have all of you here today. I want to thank everyone for being here. I want to start by thanking our students who presented in the Research Symposium. Yes. Absolutely. And in my opinion, if you want to see the impact of what the chemistry and biochemistry department at UNC Asheville is doing today, just talk to our students. And you will see the incredible work that they're doing and all that they're learning. And the Amber Alert is still going on. Okay. I'm Sally Wazaleski. I'm the chair of the Chemistry and Biochemistry Department currently. And the S. Dexter Squibb Lecture Series honors every year Professor Squibb. I'm going to talk a little bit more about him in a second, but I want to recognize those that have put in significant contributions to enable this lecture series to happen every year. So this is a endowed lecture series created because of generous donors to the department in honor of Professor Squibb. It's put on yearly. We have a committee of faculty and staff who organize the series. First and foremost, Sharon Withrow, who is our department leader, our administrative assistant, Phil Shivokevich and Ryan Steed, and myself serve on that committee. Professor Squibb is no longer with us. If you saw the picture of his partner and spouse, Joanne Squibb, on as you just entered the room. It's a real honor to have Professor Squibb's daughter, Levanne, here. So I want to recognize and thank her for being here. Because this is really a family event. It's an event that brings together department members that we sometimes only see every year or every few years, alumni, friends, guests, students. And so this is a really special event. And so I really want to thank Levanne for being here. Okay, we're good. I'm going off script, so we're going to reconnect. I do this every year, and it's kind of corny, but I love doing it, and so I want to recognize kind of who's in the room. And so if you're a student here, if you'd raise your hand. Awesome, so you can see our student participation. If you're an alumni, so a graduate of our department, there's a couple there. Yes, absolutely. I think there's some who did not raise their hands, but should have. If you're a current or former UNC Asheville faculty staff member in our department, I'll raise my hand too, absolutely. And then if you knew Professor Squibb, if you'd raise your hand. Yeah, absolutely. So a special bunch who had the real pleasure of knowing Professor Squibb. So the S. Dexter Squibb Lecture Series in Chemistry honors Professor Squibb. He served as the department chair for over 30 years, from 1964 to 1994. I'm really proud of the chemistry and biochemistry department here at UNC Asheville. We focus on students, student development as scientists. We work to provide a really modern chemistry curriculum, and we focus that curriculum on learning science by doing science, and you could see the really fantastic and cutting edge research that our students presented today. And so that's something that, that we really focus on. But all that we're doing today is built on a very strong foundation that Professor Squibb developed. So he was the founder of our department, the very first department chair. He is an award-winning teacher, a fantastic chemist. And so upon his retirement, this lecture series was created to honor his legacy and his dedication to service to our department and to the university. And so each year we honor his legacy by inviting a distinguished lecturer to campus who is a critical scientist and chemist and educator in our discipline. So I'm going to invite my colleague, Amanda Wolf, who is our GlaxoSmithKline Distinguished Professor, to do the introductions of our distinguished lecturer. Thank you.
Thanks, Sally. So it's my pleasure to introduce Ted Goodson, who is the professor, I'm going to get it right, the Richard Barry Bernstein Collegiate Professor of Chemistry and Macromolecular Science and Engineering. He's extremely interdisciplinary. Dr. Goodson received his BA in Chemistry and Liberal Arts from Wabash College, and then went on and got his PhD from the University of Nebraska. He then did 2 postdocs, one in physics. There was one at the University of Chicago and at the University of, at Oxford University. In his independent career has just been phenomenal. He's published over 200 publications. He's had over 50 PhDs graduate from his laboratory. He's mentored more than 25 undergraduates in his laboratory and many, many high schoolers as well. Ted was actually telling me today that he was an ACS Project Seed student when he was in high school. And then he also did Project Seed projects when he was at Wayne State in Detroit, and then again in Ann Arbor at University of Michigan, where he is now. So he's really big into helping students evolve from high school students to undergraduates into their PhDs and beyond in their careers. The reason that I got to know Ted was because he was awarded, among his many, many awards that he's had, he was awarded the Holland Award from the Research Corporation for Science Advancement this year. He was one of the inaugural awardees in this, and it was for his impact not only in research, but in mentoring and helping shepherd the future generations of scientists through in chemistry. And so it's really my distinct honor to be able to welcome Ted to give us our seminar today, and I'm so happy that he could join us today.
Okay, thanks for the introduction. I was told I need to stay in this spot for the talk because we have a person filming. When I lecture, I usually move around. So if I start moving, I'm sure he'll tell me. I've really enjoyed my visit today, and I've enjoyed all the discussions and the nice weather that you created for my visit here to give the Squibb lecture. And I'm really looking forward to tell you a little bit about this word, quantum, today. But before I do that, you should see the people in the group that are in my research laboratory. We have engineers, we have scientists that are chemists and physicists, and we even had a math student once, So, so everybody's interested in these kinds of projects, mainly from the kind of deep, feeling of just interest in science. And so, one of the things that I always try to remember in doing research and trying to make an impact on younger scientists is that, that science is still pretty cool, actually. There's lots of exciting things happening in science, and that, that curiosity aspect, if it still burns in you, I think you should go after it. So I'm going to tell you something, and there's a subtitle that says it's in the noise. My goals of to talk today is to tell you that, which you probably already know, the quantum age has arrived, and it's here to stay, I hope, and that you might want to think about how it affects you, actually, and what does that word really mean, right? Quantum, and so where can I find quantum? Let's talk a little bit about that. Not really any. I'm pretty sure there are no equations in this talk. Okay. I checked last night. I might be wrong, okay? But let's talk about, ideas, right? And how can quantum be applied or help us understand biology and maybe even medicine? Let's talk a little bit about those things and how they're adjusted. And so, but one area that pertains to me is how chemists can get involved in what we call this quantum information science revolution. As you'll see at the beginning, quantum has kind of been the forte of physicists and engineers, theoreticians, and I think most of them are looking to chemists for good ideas. How can we utilize some of these concepts in the real world? And so I say the future is bright. So that's what I want to tell you a little bit about today. But you've all heard this word quantum. I'm sure maybe you could have said, not only how many undergrads were here or something. Who's heard of the word quantum? Everybody should raise their hand, most people. But probably, the vast majority have heard it from something like this, right? From Hollywood. And people, in academia, they actually sometimes, they look down upon Hollywood's version of quantum. I think it's great. I mean, I think Hollywood, much better than, a chemistry professor, has the ability to reach out to the community and get them thinking about, things like how energy and space and time can actually move around, right? And it shows you that, it's been around for a while, but I would say the time, there was this show on NBC called Quantum Leap. Probably, okay, that you just dated yourself, right? Because I said this to a group of undergrads, and they're like, "What's that?" Right? That's it. And so, but anyways, Quantum Leap was a very popular thing, and I actually admit when it was out, I didn't really understand what the word quantum was. Okay, and so, but now I think the time has come that inspired by Hollywood, inspired by Jonathan Majors, that we can all understand quantum. Well, really, this quantum revolution has 3 pillars. And what I'm gonna do is tell you what the pillars are at the beginning, with not much explanation, just what they're useful for. And then really the bulk of this talk is really how chemists can get involved with this, okay? Because these pillars have been pretty much dominated by engineers and physicists. So the first pillar is that quantum can actually improve our sense of communications. By use of satellites and so on. And then the other is by I'm sure everyone's heard about quantum computing. And then the one that I'm most involved with is metrology, or measurement, or sensing. Okay, so these are the 3 big pillars of this quantum revolution. There's lots of people working on quantum computing. There's lots of people working on sensing. So let's talk. I'm going to go through that quickly, just showing you the advantages. So there's even companies now selling quantum computers. These quantum computers are down at the atomic level. So when you open up, if you're like my son, he likes to collect computers and open them up. Okay, and so now he's writing code, and he's a freshman, and you're going to see a picture of him. He's actually in our laboratory. Okay, so he can write code and so on, but he really was just curious: how does a computer work? And it's a fundamental basis that quantum computer is trying to do something different than a classical computer. And they're trying to use atomic levels to entangle different atoms, like cold atoms, like Chris Monroe at Duke and others, and they've started a company. But the point is that a lot of people might think that quantum computers are just going to try to make computations and things faster. No, I mean, the real thing about quantum computing could be best expressed by chemistry. We want the quantum computer to do what the other computer could never do. If you just want something faster for a result that you're going to get, this is a lot of really expensive research just to get it a day early, right? But there are some holdups in classical computers that they will never be able to calculate. And you want the quantum computer to do that. And the best examples, the best kinds of killer applications of the use of a quantum computer is in chemistry. Okay, and I'm giving you one here. You notice that the quantum computers on this slide are actually small, and the chemistry is big. If we could use a quantum computer to calculate the energies and the structures of large proteins really quickly, and then interpret their structure, that would be something you could not do with a classical computer. So that's the first pillar, is quantum computing. The other is quantum sensing. And so you might have seen some of these things. For example, this planet, but this country has a GPS system, right? And so the GPS system is based on these clocks that are and satellites roaming around the Earth, okay? And there's like, 20 some of these clocks that are moving around. Well, these clocks are not just your regular Rolex clocks. These are these atomic level clocks, right? And they use their timing based on atoms like transitions, energies, going through an oscillation. They're extremely accurate clocks. And the accuracy is proportional to their ability to tell you, no, you're not at the drugstore yet, right? You got 5 more miles to go or something, right? Okay. And so that accuracy turns into its precision. They call that quantum sensing. The clock is in the satellite, okay? And, they want to make better clocks, right? Because then we can, not tell where the drugstore is, but we'll tell you, oh, you dropped a quarter, right? Okay, and so that kind of research is still ongoing, and they're trying to make them small, okay? So that's your second area, is the so-called quantum sensing. And the quantum sensing I'll show you about later is going to be not only in these kinds of applications where you're using clock transitions to determine how fast and how accurate something is, but also in using materials to actually determine their energy states. The final area is this communication. This is another kind of example that Hollywood has had a fun time implementing in movies and so on. But the big picture is that with the ideas of quantum, you could make a perfectly unbeatable encryption, right? You could make an encryption that no one could ever calculate the encryption format. And so only if you had the key could you actually find the information. This is the dream, that we have a satellite system of networks and we're passing information around the globe, and only if we have the key can we actually find the information. It would be perfect, and that would be the example of something absolutely perfect. So those are the 3 pillars. People are already doing these things, like in Germany and other places, where they actually set up these networks and illustrate that this is actually possible. And then you can do things also with things with cables. So those are the 3 things. But what? I haven't told you what quantum is. I just put it out there first, right? Obviously, quantum's got some good stuff that's, it's going to make a huge impact if these things really pan out. Agreed? But what does it really mean? And so, instead of this being a physics lecture or something, just, give you a few ideas about what this word means, and you'll see then, okay, I see how this works. It's taking advantage. Well, the first, and this is not an equation, it's just an expression, okay? All right, and so the first is things need to be small. Yes, and that's the hard part. So things need to be small. Really, what that means is that when things are small, then we can have not necessarily deterministic or particles, something I have in my hand. We have waves, right? And unfortunately, because that means the wave doesn't have a deterministic, it doesn't have an answer. When you teach PCAM, students like the answer. It has a probability associated, right? So these waves have probability. They don't have answers, okay? The answer is that it's probably this. That's not satisfying sometimes, but people like me like that because it also says that the probability of other things happening is true also, right? Whereas if you have just the answer, deterministic, the particle, there's only one answer, right? So that's the first thing. If you're going to talk quantum, it's got to be small, like an electron or something that where the momentum is about the same as this ridiculously small number called h, okay? I'm not even going to tell you what the number is, right? It's ridiculously small on purpose. And when those 2 things are close to each other, then you're in the quantum realm. So technically in that movie, they should have had this equation walking around with the character, the Ant-Man, right? That is the quantum realm, okay? And so then that's the first thing. And the second thing is that, we have the idea that the world lives in a kind of classical meaning continuum of energy. If you wanted to throw the baseball at Sally before she caught it, you know what I mean? She's either got to catch it or it's going to hit her in the face. I'm sorry, Sally, okay? But technically, according to quantum, it may not hit you in the face, right? Okay, and so there's these states in quantum, whereas in classical it doesn't exist, right? You just have the energy, right? And so the resolution of that idea, when things are small, the energy is small. You have this idea of definite, quantum states, but as you make the energy big, it looks like what we would expect with baseball. You better have a mitt, the ball's coming. Agreed? But with an electron, it might hit Amanda instead, right? Do you understand? It's probable. There are no answers, right? Okay. So that's the second thing, is that we recognize things have to be small. We also recognize that the resolution gets worse as I make things big, and that the energies become closer together. But then we have this part, and this is the thing people want to talk about most. And so, so those are the actual things. You could understand a lot of quantum with just those two things. Things have got to be small, and that the energy has got to be small also. When the energy gets big, you don't get the quantum, you better have a MIT, right? But then there's this idea about entanglement. And so, people want to scratch their heads. There's some equations, but they're not equations that really describe this picture. Basically, the idea of this entanglement, which is a property of quantum, says that there are these correlations that are so strong that it's possible that the properties of one object can be totally dependent on another, no matter how far apart they are. And you can see in this picture, there's a globe there, right? And then there's a red and blue particle in one part of the globe, and there's another, right? And the other part of the globe, and it says, well, look, at the beginning, this is a quantum idea, right? And entanglement is the most celebrated idea, of course. Everybody wants to. At the beginning, the particle that's up there at the North Pole could either be red or blue. Agreed? And then the one at the bottom could also be red and blue. And if they are entangled, at the beginning, I don't know the answer. I don't look, right? At the beginning, if I don't know the answer, then they both exist at those two different states at the same time. That's a hard thing to grasp, right? So it says that this, technically, before you look at the result, number one is both red and blue, and number two is red and blue. It's only when I look at it and I make a measurement that one becomes red, and then because one became red, two has to be blue. That's this correlation, right? Or if one became blue, two must be red. It's the idea of entanglement. It exists. It used to be kind of a construct that people would talk about as kind of an abstract idea, cool. A lot of times in quantum mechanics, a lot of people like to really make philosophical statements about the results of quantum. This was one of them. And people for a long time would just kind of talk about entanglement until they gave a Nobel Prize for it, right? And they said, well, it's been done so many times that you can use these different types of correlations, and you can prove that small particles, when they're small, and you can prove that not only when they're small, but when the energy is small, that you could have this case in which you could have two particles, like two cold atoms or two photons, and you could illustrate these entanglement correlations that can't be explained by any other means. And these three gentlemen did that. So there you are. There's your crash course in quantum mechanics. Isn't that really all you need to know? It has to be small, and the energy has to be low, and that there's this funny idea of entanglement. So now you can start to think, well, geez, okay, here are two cold atoms, and they're apart from each other, but you can see when one becomes pink, the other one becomes blue. They're constantly exchanging information. And that's where this idea about quantum information came from, right? Is that you have two things that are separated, but their correlations are so strong that they must be exchanging or sharing the information in practice. So my area of research is in the use of something called entangled photons. These photons show these interesting correlations, meaning that I'll show a picture later, is that I'm going to utilize these entangled photons to do things that, quantum sensing kinds of things that you cannot do with just regular garden variety photons. But let me just show you. For example, this paper was published in Science in 2017. It's a group from Penn, and it's published in Science, which means, it's completely true, right? And so that they sent up a satellite and illustrated that you could show this entanglement over 1,200 kilometers. They illustrate, they set up an experiment. One thing is in one city in China and the other's in another. Okay? These ideas are strictly, were strictly abstract, and now people are thinking about ideas of doing sensing from space, right? So, and this goes beyond just those abstract discussions about what quantum should be or could be. These are people building hardware to actually do demonstrations. And so we had a project with the Department of Defense some time ago with some colleagues in Ann Arbor and on detecting aerosols and so on. So, but remember, it's got to be small. So if you had a huge signal, if you were trying to do some measurement, somebody measure some fluorescence, I think, for their assay of detecting if a particular agent had bound to, I guess, an enzyme. I can't remember who was telling me that. Or if you had some measurement in which the signal was huge, you probably don't need quantum, okay? It's only when things are small that quantum, and that's the point, isn't it, right? You're trying to do things that are highly improbable, so the signals are very small. They're in the noise, right? And so there's a famous quote from my postdoc advisor at Oxford, and so he says, "Noise is truly ubiquitous. It confronts us every day in the form of unwanted audio, electrical, or optical disturbance. To some people, noise is static, and to others, it's snow. It's everywhere. And although noise is often white, it makes most people, scientists and engineers, see red." And so that's the truth. And guess what? If you really want to do something in quantum, in most cases, the signal's in the noise, right? And that's what you're trying to beat. You're trying to beat something. If it's way above the noise, you don't need all this fancy equipment and so on, right? But you're trying to beat something that's relatively small, and it's in the noise. And that's where the whole quantum idea starts. So you can talk about the number of photons and so on, and basically this just says that, what the number of photons that come out of a laser beam is basically equal to, some number n. But the standard deviation, the error in the number of photons that come out, is also equal to n. And so I call that the standard quantum limit. It's basically a light source or a laser source is actually quite a noisy piece of equipment. But so many photons, you don't really care. And so in the early days, people were trying to reduce the noise in light beams because they knew that the fluctuations in the number of photons will kill all these quantum measurements. So then people said, well, what if I could utilize some kind of idea where I have waves and I'm making my circuit, my chip circuit and so on, and there is a small gap, and they're talking, in the realm of nanometers. And if I use energy or light waves that go across this and I use normal light, the noise will be so high here in that gap in my circuit that everything will die. But if this noise is actually of the same, range or the same magnitude as the quantum signal, is it possible that the signal then now, the quantum signal, can dominate this process? So if you just use regular kinds of things, and this is an example of how the chip scale technology is trying to use quantum in new kinds of chips. Not only are you trying to use quantum to get more calculation, more calculation of things that you cannot do, not just speeding things up, but you're also thinking about the actual hardware that if you could use the actual microwaves that you use in a quantum computer, if you could use them with less noise, could you actually even do better calculations? And so these ideas are bolstered by this more recent kinds of processes that the government is doing with this CHIPS and Science Act. They're trying to actually not only think about just new ways of making chips, but also new ways of thinking about chip technology using quantum. But anyways, here's this entanglement. So now you've learned it's got to be small. The energy's got to be small. And there's this idea about entanglement. It's still kind of scratch your head about a little bit. But if the noise is bigger, if the noise is small to begin with, then the quantum effect can be strong. But in many cases, the quantum signal is in the noise. And I just already told you that communication and cryptography, they could certainly benefit from it. My research has been mostly to actually use nonlinear spectroscopy. And without telling a lot of details, we generate entangled photons. You might say, well, how do you make two entangled photons? Well, I mean, just like in a lot of things in optics, you got to have the right crystal. So these crystals are generally made at, well, just to be honest, it used to be all made in China. Now a number of companies, certain laser companies, are starting to make these crystals. But this beta barium borate crystal is the magical crystal. What does that mean? It says, well, it can do this process called spontaneous parametric down conversion, just a bunch of words. But when I take a laser beam and shoot it through this crystal, and if I'm at the right enough energy, it will generate these two photons that share these interesting correlations. And it suggests that entanglement is a natural thing. What does that mean? It means that force and gravity, they're natural things. Entanglement is a natural thing. We just don't have good ways of detecting it, but it is a part of nature. And so, but this is how you do it in a laboratory. And there's all kinds of ways to make entanglement. So you can use different kinds of materials, you can use different kinds of crystals. And so in our research, we generally use these different types of nonlinear crystals. We've had people generate entangled photons when they started in high school. And we've had research professors join the lab and struggle and eventually ask the high school student how to make entangled photons, right? And so it's a knack, and it's really just a lot of optics. But how can chemistry get involved, and how can we do something? Well, it turns out that the interaction of entangled photons is with organic or molecules' electronic states is different than the interaction with regular photons. Who knew? It means that somehow those correlations imprint on the electronic states of these molecules. So when you think of a regular classical kind of interaction with a photon from a laser, you would usually think of some excitation of usually those darker lines on this picture. But my research has really been trying to explore, we're still kind of at the beginning. We have lots of research that we've done, but we're still trying to explore that statement that the interaction of entangled photons with electronic states of molecules is different than with classical photons. And we've done a number of things. We've done imaging, we've done spectroscopy, but we still are kind of trying to understand that process with both experiment and theory. But looking to the future, and that's more research, and I should always preface a lot of these applications, they're really at the research stage still. Let's be candid about that statement. Science and Nature publish great papers, but don't look beyond the fact that these are still research projects, okay, in many cases. And there are a couple of things that are probably closer to the market, but in terms of research, with entangled photons, I would say that's really a research kind of area, which should be explored so that we can learn more. But there are other tools besides entangled photons to utilize quantum. And really, a lot of these involve this kind of magnetic properties of materials. For example, you've probably seen this on television, but with quantum and with the idea of this, entanglement, the idea of, getting some kind of quantum tunneling, you can measure extremely small magnetic fields, and extremely small. There's something called a SQUID, or so-called a superconducting quantum interference device. It basically is a measurement that can measure a quantum level kind of measurement of magnetic fields. People use these squids to measure very small waves. I don't know if you can see the picture in here, but very small magnetic waves that are emanating out of my brain as we speak. Okay? And they actually have devices. And so you can see here was a magnetometer back in the day. Look how big that is, right? And then this is optically pumped magnetometer. This is the first single channel optically pumped magnetometer. This is the first wearable optically pumped magnetometer. This is not anything complicated. I said you got to be small. You got to have small energy. This is saying the waves of the magnetic field coming out of your brain are in the noise. So use quantum, right? And then now this 50-channel whole head optically pumped magnetometer scanner, it's a product. So, and that's a great application of those three principles that I was just saying. Another area in the magnetic regime that people talk a great deal about is that, and chemists can get involved, is in looking at different types of magnetic pulses in fetal patients. For example, there are maternal conditions that can place an increased risk of fetal development of cardiac arrhythm, such as long QT syndrome. The QT is the actual pulse of. And so this arrhythmia places the fetus at high risk in developing different kinds of diseases. One of them is called Toussaint-de-Pont, which becomes incompatible with life and sadly leads to stillborn. And this is when the fetus is still in the mother. And so using new technology and quantum magnetometer, it's possible to distinguish the electrical pathway in the fetus that's moving around, and its heart's moving around, inside the mother. And so this was a report here, and this is an example that actually exists. And so the fetus is in there. It's measuring really, really small signals. And it notices that when it has this kind of arrhythmia, it's probably not it might make a decision by the physician to actually treat the patient differently or to have an early birth, because actually keeping it inside is a great risk. But when the signal is small, the quantum dominates. And so this is an actual product, right? But this is an extremely expensive instrument. Another area is that people interested in looking at cells or nitrogen vacancy quantum sensing. And so looking at very small things and looking at the different properties of cells who have very small energies, very small magnetic fields, very small changes in pH, and it takes advantage of, again, some idea about this so-called quantum entanglement, where you have a nitrogen vacancy in a piece of diamond, a tiny piece of diamond, and you're going to utilize that to sense differences in the magnetic field. And so people have set up these kinds of things, and they can actually investigate changes on a very minute scale in live, animals. Okay. So so areas that I'm more interested in is how we will use quantum to understand how to do spectroscopy and microscopy. And that goes back to the idea of quantum entangled photons. How can we utilize these entangled photons to do imaging better, this is an example of paper by Warwick Bowen in which they use Raman, and you can see the image quality will be enhanced by the fact that it's already a very small signal, and that the quantum can actually get this enhancement. And that, in his case, uses the squeeze states. And in our own lab, we were able to get these images using entangled photons of breast cancer cells at very small numbers of photons. Another area in which the quantum can actually use is that in the case of using entangled photons, you only need to use very few of them, or a much smaller number, which is actually good in biological situations in which you actually can use very long scanning, and you can actually detect things over very long times. So it has a wide range of applications. So what I've told you so far is that the three pillars are going to be there, but I see some opportunities for chemistry. I see them in the sensing area, and I gave you some examples in the biology area as well. But chemistry is just nestled to actually take advantage of some of these opportunities. Which brings me to kind of this message that the QIS field could really benefit from the chemistry community, and I think the chemistry community could benefit from the QIS field. And so this is a report that was written by a committee from the National Academies, and it was funded by the National Science Foundation and the Department of Energy. And it really says, well, we understand those three pillars. Those mostly are physicists and engineers. What about chemists? And so what could QIS and chemistry do? And I kind of tried to give you some examples already, but the urging of more cross-discipline research and other things was the reason for such a lengthy report. And if you're interested in downloading the report, there's the scan there, but you can email me as well. And the idea was to identify opportunities at the interface of chemistry and quantum information science. And there were a distinguished group of people on this committee, all in the quantum space, interested in how chemistry could play a major role or a bigger role in quantum information science. So overall, the future holds, at least from this report, and I hope from the National Science Foundation and Department of Energy, the future holds a few areas of expertise that chemists can get involved in this area. And so the first, of course, is they can design and synthesize new molecules to be used as the bits in the quantum computer. So remember I said, the quantum computer that the company at Duke is selling, and they're made with these cold atoms, right? So there's an idea that you can actually use molecules to be the bits of the qubits of the quantum computer. And so, and then you could scale it much faster. You could have the scaling laws of how these could be working out. The second area is that, chemists are really good at measuring things. And, is it possible that with said molecular quantum systems, could you measure and come up ways of controlling the quantum system? And then finally, there are some new computational approaches for scaling qubit design, coming up with new algorithms and so on. Those are the basic three scientific areas that quantum information science is moving towards in the future. So the first is, of course, that you could create new materials. And so, there were some colleagues on the committee, but also just in the field, have illustrated that some of these inorganic materials could be used as, basic qubits in a quantum computer. And they have some success. There's also some success that's happened in Europe in the actual trying to use molecular or synthetic organic chemistry or synthetic inorganic chemistry to determine if these materials can be used as the bits in a quantum computer instead of the very expensive atomic at 3 Kelvin, atoms at 3 Kelvin. And so they have had some success. They're still at the beginning. there is a need for more chemists to understand these processes and try to reduce this issue of this kind of environmental interaction onto these materials. So that's the problem, unfortunately, with chemistry at room temperature, is that the environmental effects will usually dampen the quantum effect, okay, or decohere. And so they're trying to figure out ways to do that. There's been a number of different types of materials and organic materials as well. Those were inorganic, and these are organic. And then, of course, the fabrication, chemists can get involved in the fabrication of these systems as well. In terms of looking at fabricating new devices based on materials of synthetic, that are made synthetically, chemists are the experts. And so, how could they actually get involved in the creation of new qubits, not just in the making of new molecules, but the creation of the devices themselves? Then there's the measurement. I think I've showed you the picture up here. You can talk about the use of entangled photons. You saw some examples of using magnetic entangled, spin, and other kinds of examples. Chemist is a measurement scientist down deep. And so we really think that they can make strides. But in terms of the overall picture, you can say that, chemists actually have been thinking about how this field, has a culture of, as I said before, and I've said again, of mainly physicists and engineers. And so we think that the use of chemistry, not just the chemicals themselves, but the actual way chemists think about problems and how they teach problems can actually help the workforce, the QIS workforce, in order to have a competitive US front for quantum information science. So development of a diverse quantum capable workforce should be a goal, and is a goal, of the NSF and DOE. And there's a big aspect of QIS and chemistry education. So right now, there are not many curricula that have anything to do with the QIS at the moment. But I guess the point is that while you don't need to have a PhD in quantum physics, chemists have skills that can be useful in quantum information science research. And, skills like, first, knowing how to make molecules, but also knowing how to separate molecules, how to purify molecules, how to work with high vacuum systems, how to work at low temperature, and so on, right? All of these skills are necessary to work in this space. And, somehow the curriculum and the development of the curriculum can be improved in the future to try to inspire more scientists, young scientists, to join this field. There are some barriers to entry. Probably when I was starting in this area, the barriers to entry was that, I did a postdoc in physics mainly because thinking about these things in a chemistry department was not really feasible. Okay, and now we need to kind of reduce that barrier so that chemists feel very natural about thinking about these processes. They still don't need a PhD in theoretical physics, do they? But they do know, and we all know, we need new materials. We need small things that can transfer energy, magnetic waves efficiently, new ways of detecting entangled photons, and those are all materials. So we need to reduce those barriers of entry. And then finally, the economic development is still relatively slow for QIS in the country. And so, and that could be connected with my statement that, this is still research, right? And so, it's important that you develop some sort of economic development in the QIS, but you don't necessarily have to force it, So the chemistry QIS market is a largely untapped possibility, possibly for some young person in the audience today, making a business out of new molecule qubits, partnering with a large chemical company to make substrates for quantum, devices. It's an untapped, opportunity for chemists. The physicists and engineers, they're not accustomed to talking to chemical companies, right? Okay, and so it's an opportunity, and like the Chipson scale and so on. Okay, so I'm going to kind of summarize what I've talked to you about and what I think the future is. And so first of all, let's summarize. You know, quantum is in the realm of the small, and it really is only, I would say, useful when it's within the noise. Okay, and then secondly, those are the three pillars. You got quantum computing, sensing, and communication. They form the three pillars. You know, everybody kind of knows those three pillars, but you know, there are several good examples in which a quantum sensing application in chemistry or biology has been illustrated. And so we don't necessarily have to follow the three pillars, right? Chemistry usually fills in that quantum sensing pillar, but there's a great opportunity for chemistry. But this is still research, okay? A lot of these things are still at the research stage. Probably that example I gave, a couple of those examples with the magnetometers are closer to you know, the market. Some are being sold, and they are technically quantum devices. But you know, the whole entangled photons and things, they're still at the research stage, making great progress. But we still need to ask lots more questions to understand processes much better. And so this is a technology for all scientists, not just physicists and engineers. And so the special place for chemistry is in QIS is their ability to understand how molecules, not only how to put molecules together, but actually how molecules interact with each other, how molecules can actually do certain properties, their electrical and optical properties, how molecules can be used to fabricate devices. Chemists know these things. It's an untapped field. And so I suggest that the future, with the new developments and with a new and diverse workforce, I suggest the future is bright, as long as people can consider the fact that we still need to do more research, more collaborative research, understand that other parts of the world are doing quite well in this research too, and that we can learn from them as well. So please join us in thinking about a QIS field, right? Again, you don't need a PhD in particle quantum physics. You need an interest, right? And you'll see where it drives you. So let me close by acknowledging, you know, some of the people that work with me. Even though I try to make this as a general talk, my research really is on the spectroscopy. And, you know, we have senior scientists and postdocs and graduate students and undergrads in the group, all interested in various aspects of how molecules work by use of laser light. Either the laser light is your regular classical light with an ultrafast pulse, or your laser light is some kind of entangled photon, or your laser light is in a microscope or something. And so, I want to acknowledge my excellent group, and I want to thank you for this excellent day. I hope you learned a few things in this talk, and that you have lots of questions.
Thank you so much. It's time for questions. And in the tradition of the department, we're going to have student questions first, but I ask you to come to the microphone so we can hear your question. So come on up, Isaac.
For quantum entangled photons, is there a specific wavelength of light you're looking at? Is it like in UV, or is it like more visible?
Right, that's a great question. So the original crystals, it depends on the crystal. Very good question. So the original crystals were kind of in the near infrared region, 800. And it happened to be a lot in the 800, and then later in the telecommunication wavelengths, like 1.5 microns. But there were a lot of them at 800 because people were using mainly titanium sapphire lasers, and they are about 800 nanometers. But you know, in these biological and chemical kinds of applications, you don't necessarily want in the 800. You want something in the visible and so on. And that requires new kinds of crystal technology to generate entangled photons in these different wavelengths, right? And so there is a kind of dispersion. There's a spectrum of the ability of the crystal to do the magic, right, and to make the entangled photons. And it's not continuous across the spectrum. And so, so what you do is you find a crystal that is in the area that you want to work, and then you try to optimize the number that you can make. Good question.
I hope I sound all right. Thank you so much for your talk. This is actually the first time I've ever heard of a cold atom, and I'm not sure if this is necessarily the 3 Kelvin atoms you were talking about. Could you quickly explain what they are and why they're so useful to these quantum studies?
That's a great question. So, you know, really, the cold atoms are going to be your qubits, okay? And they sometimes they use rubidium and so on. I think this is what is here. So essentially, they make this array of these cold atoms. Cold meaning they cool these down to ridiculously low temperatures, okay? And then you're going to have some excitation of these atoms. And guess what? These atoms are going to get their energies entangled, okay? And so now, if I look at this array, right? If I excite one of those cold atoms in that array, then technically the others get excited as well, yeah? And they're all stay put because they have no kinetic energy, right? It's less than 3 or 1 Kelvin or something, right? Okay, so so when the excitation happens, it gets delocalized or entangled throughout them.
Thank you so much.
Mm-hmm.
Just for fun, how real can you quantify the science in quantum leap? What do you find to be the most probable? What do you think is not the most probable?
Sometimes there's not one answer. Okay, that's a great question. I really love it, right? So, all right, so let's go back to this, this picture. You know, it's about probability, right? And so, yeah, you should doubt it. I just told you, I mean, okay, the particle on the left, it's like a baseball, right? And then and the wave on the right is not necessarily a baseball, right? It's a wave now, okay? And so you should doubt it. Well, okay, I'll give you a technical answer, okay? When that energy, the momentum is close to h, I can quantify it exactly. I know the probability, right? But when things start to get a little big, but they're not big, but they're not, you know, they're not a baseball, but they're maybe bigger than an electron or something. Now the quantum is getting a little fuzzy, right? Okay? And so how do I quantify that? And when you measure these probabilities, right, you actually, no, I don't have one answer, right? I have a probability. And maybe that's good. I have the probability that other things may exist, okay? But if the probability is high, then the answer is, that's the answer to your question, right? And so that actually, your question could be interpreted as the question of metrology, right? And so that's the hard part about quantum. You're trying to measure something beneath the noise, right? And this whole area of metrology really relies on people making good measurements, right? It's hard. And so you set up different kinds of scales that you can actually quantify, right? And so, yeah, I mean, it's a probability thing, right?
I wanted to ask what the image was on the quantum physics slide. There was an image that was C. I think it was 2 slides back, possibly.
Oh, before. Image?
Yes.
Image.
That one. Found that slide just ahead of this one.
Oh, you mean this image here?
No, like forward. Couple,
Oh.
like that one.
Oh, okay.
What was the C image at the bottom in the lower right?
Oh, okay. So this is saying that this is the cold atom kind of idea, right?
Okay.
And so this is saying that they can actually make an array so that you know what's on the right here. That should look familiar if you ever tried to open up a computer. And so they're going to make one of those on the B with cold atoms, okay? And then down here, say, well, how do you trap them? They have to trap these atoms. They're moving around, right? And this is illustrating how they trap cold atoms.
Thank you.
You mentioned there was a group of people trying to take quantum and do it at room temperature instead of colder temperatures. Is colder always going to be more effective for understanding quantum studies, or is there like a sweet spot of temperature?
Well, and that's one of the advantages of chemistry, right? So if you're just going to use atoms, yes, cold is better, of course, right? Because if you use atoms, then these quantum states the probability is really high, right? But chemistry offers something else, right? And so the scaling of different interactions, making macromolecules that are coupled strongly to each other, making all these different states in molecules that could be done at room temperature. And so that is the promise that chemistry could offer, right? Is that in the future, we won't be using necessarily just cold atoms, because actually some of the same atoms that they're using in the cold trap here are some of the molecules that people are making, and they're utilizing the host and the interactions between other molecules to essentially do the same thing that the cold atom is doing. And that's the goal. It's not there yet, but we hope that chemistry can do that, right? So you see this picture here. You know, this idea is that you could make molecules, make crystal structures that now have multiple atoms, right? And, you know, is it possible that I could actually use some interactions between the molecules to, you know, to offset the environmental effects that happen when you raise the temperature?
Thank you.
I didn't mean to exclude non-students from asking questions, but I'm very excited by all of our student questions. We do want to honor time here, so if there's any remaining questions, Kyle's going to go next. Please come up. If you come to the microphone, that would be wonderful. And maybe 3 more questions will be perfect. Thank you.
Hi there. Thank you for the presentation. When utilizing these sort of quantumly entangled photons, you might have mentioned it earlier with the cold photons being trapped in those computers. How are they sort of, I'm guessing might have been trapped because of the cold, but how are they necessarily trapped and like separated from one another? Just general question.
Okay, great question. And so first, the atoms are the ones that get trapped. The photons come out of that crystal. So let me see if I have a picture for you. Let's see. Yeah, the photons come out of the crystal, and you hit on the really important point. Unfortunately, these photons that come out of the crystal, they come out in an incoherent manner. They're not like a laser beam. And that's another reason to understand why this is a natural process. It happens spontaneously, right? So the photons are incident from the laser onto the crystal, and then these entangled photon pairs come out spontaneously. But most of the photons are a complete loss, right? Only a very small number of them will come out paired, and then you can do these experiments and change the polarization of one and see how the other one changes and so on. And so they come out in a very incoherent manner, which is a problem for us trying to do imaging. So you kind of hit on a really important point, right? Is that, again, if you had a huge beam of these, you would miss the advantage of this entanglement. You'd miss the quantum part, right? No, you only have a small number, and they're actually coming out in an incoherent manner. So you got to focus them and then put them onto the sample and so on, right? And so unfortunately, the number is small, but positively, I mean, and on the other hand, it's good that the number is small because that's where the quantum effect will show. And so, yeah, they're incoherent. They actually look kind of like those two cones. They come out in this cone. You can refocus them and so on, but they're not laser beam. Good.
Awesome. Thank you.
Mm-hmm.
First of all, Ted, thanks for a great talk.
Oh, thank you.
I have heard the term collapse of the wave function, and I was wondering if that referred to the inability to calculate probabilities for the entangled photons.
Uh-huh. Yeah.
Is that
I'm
what
going to
that
try to
refers
get there
to?
for you. Yeah. So the collapse of the wave function is a great kind of. You could use this here. Forget about the equation. I'm sorry. Okay. So look at that picture. And so look, the one up in the North Pole is both blue and red, and the one in the South Pole is blue and red. And so. And they are blue and red at the same time, okay? And their wave function is a superposition state, or a combination state, if you want to say that, of blue and red, right? But once you make the measurement, once you make an observation, this is the language, right? That wave function will collapse onto an answer, the one with the highest probability. And so, which in this picture, for number one, it's the red, and for number two, it's the blue. Do you see that?
Thanks a million.
And so, yeah, and so we still use that language, collapse of the wave function. Most people use the word now decohere, right? So it means there's some kind of coherence, some kind of correlation, some kind of thing happening between these two entangled photons, and you like it, it's going to help you. But once somebody makes a measurement on one of them, that coherence between them decoheres, or it's halted, and now I just have two photons that don't know about each other.
So I have 3 questions. I'll ask just 2 of them, and the first one has to be yes or no answer. Okay, so when I was a kid growing up in Kansas, which is south of Nebraska, so we didn't know as much as you guys did, I was taught that there were fundamental forces such as gravity or Coulombic charge attraction. Would you contend that entangled photons is a fundamental force?
It's natural.
Okay.
Right?
The
And
second,
so,
yes or no?
No. You use the word fundamental. I say natural, right? Like Newton said, there's the natural philosophy, right? So
Well,
this is natural.
Right, well, that you could use natural instead of fundamental.
Yeah.
The second question is, the picture you had with a ground state and then an excited state and then some dotted lines for states in between, maybe?
Yes.
So when I taught PChem, we would have these 2 photon events where the first transition was to a non-existent state. So it wasn't a rotational state, wasn't a translational state, wasn't a vibrational state. It was a virtual state. Is that what these entangled photons are doing?
So, yes. And I didn't want to actually talk
Okay,
too much
that's
about
yes or no is fine.
Because we were talking about that at the meeting in your office. Okay, so it's written here, right? Virtual states, I guess, right? So I guess for me, my personal interest in all of this is to say something about how the interaction of entanglement with matter, with molecules, with chemistry is different than the interaction with classical physics, right? And so the way we have done, and we've written these papers and we've published a lot of things, is that we've done this so-called entangled 2-photon spectroscopy. And there's still lots to be learned about the process, but the whole idea is that in the typical case, without entangled photons, you would imagine that the excitation of that first photon in the 2 would excite some virtual state that actually has no oscillator strength. And so
the third question is political.
okay.
So on the CHIPS Act, do you have anybody with expertise in QIS that is helping decide who gets funding from the CHIPS Act? And if not, why not?
Oh, okay. So the National Quantum Initiative, I think it's mentioned in here. The National Quantum Initiative is, from the Office of Science and Technology, and so they have, made it clear that it's the CHIPS and Science Act, and that the science bit was going to have some contribution to quantum. And, the whole rollout of the CHIPS and Science Act is quite a complicated thing. Michigan's involved in some aspects of it, but how that will play out, I don't personally have information about that. I guess to me would be a goal would be that, certainly this country needs new developments in chip technology to remain competitive in that space, and that has nothing to do with quantum. But I would say, thinking about the future, 20 years from now, what if someone started to use different kinds of chips, right? And doing a little research in that area and exploring that area probably would go a long way. And so we'll see. We'll see what happens with the resources.
Please join me in thanking Dr. Goodson for his talk today.